take a moment and try to imagine a world without energy on demand. No lights to brighten your evenings, no heat to cook your food with, no vehicles to propel you from one location to another. It's difficult, isn't it? That's because, as a species, it's been in our nature all the way back to prehistoric times to quest for sources of energy. From the first moment that humans harnessed fire, that quest was underway. And it continues to this day. Our relentless search for the energy that we need to improve our lives has led to the invention of many methods of extracting energy from our environment. Although we have devised many diverse technologies to accomplish this, they all share at least one common need: fuel. A fuel is any substance that releases energy, either as work or heat, as a result of a chemical reaction with an oxidizer. Now, by that definition, just about everything around us is a fuel in one way or another, as long as a sufficiently strong oxidizer is being used. But a more convenient definition for our discussion is a material that releases energy in a chemical reaction with oxygen. Since oxygen is abundant in our atmosphere, it serves as the oxidizer for most fuels with which we're all familiar. Of course, the classic examples of fuels are those which we combust in air, and almost certainly the first of these was wood. To put things into more chemical perspective, wood is essentially the biopolymer cellulose, which we've discussed in detail already. Now remember that cellulose is a carbohydrate polymer. It stores great chemical potential, but it's chemically too tough for our bodies to use it as an energy source. But expose that cellulose to oxygen from the air and sufficient heat, and a reaction will most certainly take place. Oxygen from the air combusts the cellulose fuel, releasing large quantities of energy. Prehistoric man and modern-day people alike have made use of this reaction for the energy needed to cook food and heat their living spaces. But wood is not the only fuel that has helped to shape the society that we live in today, not by a long shot. Some archaeologists estimate that humans were using oils from the ground as fuel somewhere around 6,000 to 10,000 years ago. By the time of the ancient Greek and Persian civilizations, a thick, black, flammable substance had been discovered and put to regular use. The Greeks called this naphtha. A more modern term would be pitch. You might recall that this is the material that the Spartans used to ignite sulfur, creating what might have been the first chemical siege weapon ever used. On the scale of great discoveries that changed the human world, the discovery of naphtha is just one notch lower than the discovery of fire itself. Not because it burns any differently than wood, but because it's a liquid, more easily transported and stored because it takes the shape of its containers. Also, as we're about to see, it can serve as a source of a number of different fuels, so versatile and powerful that they serve as the basis for most fuels on which we rely even today. But naphtha, or pitch, wasn't always the preferred fuel of mankind. Near the surface of the Earth, it's exceedingly rare to find. So even though it was useful as a fuel product, there simply wasn't enough of it to go around. So man turned to other sources of flammable liquids to use as fuels. For centuries after the discovery of naphtha, the preferred fuel for lamps and other devices requiring energy was the oil of plants and animals. Olive oil and whale oil were particularly prevalent in lighting technology from the times of ancient Greece all the way up to the 1800s. These naturally sourced oils were a favorite for centuries because they could be collected in sufficient quantities to meet society's needs at that time. Of course, in today's world, the term fuel almost certainly conjures up images of gasoline, kerosene, diesel, and the many other classes of liquid fuels that we rely on to move our vehicles, heat our homes, and prepare our food. Sometimes we turn to compressed gases as well, like natural gas, which is essentially methane, and sometimes we use propane. These fuels range from lighter-than-air methane to denser-than-air butane, from our culture's motor fuel of choice, octane, to diesel and kerosene, which can sometimes freeze on a cold winter night. Now, as diverse as their properties are, this remarkable group of fuels all come from the same source material, petroleum. The birth of the modern petroleum industry can be traced to Titusville, Pennsylvania in 1856, when a retired railway conductor by the name of Edwin Drake found a deposit of this material. Now, in truth, Drake often gets the credit for the discovery of petroleum in spite of the fact that its existence was actually known as early as ancient Greece. Now, what Drake really discovered was not petroleum itself, but a massive underground deposit of it. A supply so huge, so apparently inexhaustible, that it caught the attention of one of the most iconic and opportunistic businessmen in the history of the world, John D. Rockefeller. With a massive supply of oil discovered and a dwindling whale population to supply oil, Rockefeller and men like him saw an opportunity to create the next great fuel. But what is petroleum? How is petroleum formed? And why does it seem to accumulate only in certain regions of the world, like Texas, Pennsylvania, or the Middle East? Well, the answer is that the creation of petroleum that we pump up from the ground and ultimately turn into fuels that you and I use every day started on its chemical journey a few 100 million years ago. Let's take the example of Texas, with its famously productive oil fields. Now, when we think of Texas today, we usually think of a dry, rugged terrain, the sort of terrain that doesn't look very conducive to the development of sea life. But 200 million years ago, in the Jurassic Age, the land that is now Texas looked quite different. It was an inland sea, teeming with sea life, much of it plants and microbes. When these creatures died, they sank to the sea floor and became covered with sediment. Now, as biological matter decays, entombed in sediment and rock, oxygen can't get in to play a role in the decomposition like it does at the surface of the Earth. So this carbon-rich matter decays, unable to form compounds like carbon dioxide as part of the process. Now, instead, decay products without oxygen tend to form, and among these are long-chain hydrocarbon molecules, the likes of which we investigated in our lectures on organic chemistry. So, slow, anoxic decomposition over millions of years produces underground deposits of hydrocarbon-containing material. Now, at the same time, sea levels began to recede, eventually exposing the seafloor, much of which we now call Texas. So pools of carbon-rich oxidized material were now ready to be discovered by man. Now all we have to do is find it, dig it or pump it out, and burn it in the presence of oxygen to finish the process and extract the energy left behind by our microbial Jurassic friends, right? Not so fast. Petroleum is a highly complex mixture of hydrocarbons and other compounds. And remember that it comes from the decay of organisms entombed in the ground. So the nitrogen, sulfur, and other elements that made up those organisms is trapped also. Now, entrepreneurs of the late 1800s discovered that petroleum could be separated into materials of differing volatility through the technique of distillation. You may recall that we discussed this technique when we encountered hydrocarbons for the first time in our organic chemistry discussion. Distillation can be used to separate hydrocarbons based on their volatility, which is closely related to their molecular size and shape. This process can be used to collect natural gas, which is primarily methane, and other familiar flammable gases like propane and butane, as well as some familiar liquid gasoline, comprised of hydrocarbons with about 5 to 12 carbons per molecule. It's also good for getting diesel and kerosene, each made from hydrocarbons of about 10 to 15 carbons per molecule. Petroleum distillation was a very effective technique for producing usable fuels from complex petroleum mixtures, at least at first. When used as a lamp oil or a heating fuel, only a certain level of purity is really needed. Even in its earliest forms, kerosene seemed downright pure compared to those messy, sometimes smelly whale oil alternatives. But modern engines and other devices require more refined fuels, both for more predictable combustion properties and for cleaner operation. And as millions and millions of us began relying on fuels like gasoline and diesel to move our vehicles in particular, it started to become necessary to get some of those uninvited guests in our fuels out of our fuels. One of the most undesirable visitors in our most popular fuels is the element sulfur. If you drive a diesel vehicle, you're probably more aware of this than the rest of us. As you approach the pump, you always notice that the sulfur content of the fuel is reported very clearly for all to see, ensuring that the fuel you're pumping contains no more than the amount of sulfur allowable for your engine design. Just about any crude motor fuel is going to contain a certain amount of sulfur, and we want to get rid of that sulfur because consider what happens when we have, for example, a molecule of this, in this case, octane thiol. So this would come from gasoline, but it could come from, for example, diesel as a larger molecule like cetane. Now, if this molecule is burned, it's going to generate sulfur dioxide or sulfur trioxide as one of its combustion byproducts. And that's environmentally devastating. So to attempt to mitigate that, many refineries, either voluntarily or in most cases because of the law, will run this through a reactor that removes this sulfur from the fuel. And here's how it works. The fuel is pumped through a very high-pressure reactor that contains a special metal catalyst that allows hydrogen gas, which is part of what's supplying that pressure, to react with the fuel that has a thiol functional group, that's a sulfur. In this reaction, a molecule of hydrogen reacts to create now octane, which can be burned much more safely without doing as much damage to the environment. But it also forms a molecule of H2S, dihydrogen sulfide, which, although it is now removed from the fuel and therefore your process of being combusted in your engine, has to be accounted for in the remaining processes that go on within the refinery. As we're about to see, this little guy right here can cause some real trouble. The desulfurization of fuels is, of course, beneficial to your engine and to the environment, as production of sulfur oxides that would have been released into the environment are largely avoided. Now, the downside to this process is that it produces a tricky product of its own, H2S, or dihydrogen sulfide. This is weakly acidic with a pKa of around 7, and dihydrogen sulfide can react with many metals commonly used in the construction of desulfurization reactors. Think back to our discussion about the activity series. Iron can be oxidized by protons, right, from the protons in acids. And in this case, the oxidized iron combines with the sulfur removed from the fuels to create iron sulfide. This is a weak, brittle material that's purged from the reactor lines by moving gases as it forms. No one can attest to this fact better than the residents of Woodcross, Utah, where a reactor serving another purpose at Eagle Creek Refinery exploded catastrophically in 2009. The official U.S. Chemical Safety Board investigation found that the cause of the explosion was deterioration inside of the reactor caused from previous use in the desulfurization process. The pipes in the reactor had been so weakened by their reaction with the dihydrogen sulfide that they could not withstand the pressure of the new process they were being used for. The result was a devastating explosion. But diesel fuel isn't the only type of petroleum distillate that requires chemical treatment before it makes it to your local filling station for use in your vehicle. Gasoline also undergoes additional chemical treatment after distillation to improve its performance in engines. In this case, I'm talking about the well-known but often misunderstood octane rating of gasoline. Gasoline engines in particular can be very fussy about the exact detonation properties of the fuel that they use. This means that even from one gasoline engine to another, different formulations of that gasoline are necessary for proper performance. Gas engines, unlike their diesel counterparts, rely on a spark from a spark plug to achieve detonation. An engine cylinder is filled with a gas-air mixture, then compressed by a piston prior to detonation. A spark initiates combustion of the fuel at just the right time, and the resulting expansion pushes the piston back to complete the second stroke of the four-stroke sequence. Now, the potential problem is one related to Gay-Lussac's law. Remember that pressure and temperature are related. So, compressing a hot mixture of gas and air can increase its temperature even more and cause detonation itself before the first stroke of that piston is complete and the spark plug fires. This causes the engine to malfunction and possibly even become damaged. Now, there's a distinctive sound made when this happens, like a knock or a ping. And the solution to this problem is to simply use fuels that are adequately resistant to detonation under the heat and pressure conditions that a particular engine generates. Now, that might sound complicated, but there is a very useful general rule about hydrocarbon structure and how it affects resistance to detonation. The more branched a hydrocarbon is, the more resistant to detonation it will be. So, compounds that make up gasoline, primarily hydrocarbons from 5 to 12 carbons in length, are often passed through special reactors with metal catalysts designed to promote isomerization reactions that lead to more branched molecules. But that leaves the question of how to report on the detonation resistance of the fuel blends before and after this isomerization process takes place. Well, recall from our lecture on organic chemistry and hydrocarbons that octane alone can have up to 18 different isomers, some highly branched and others only slightly. Add to that hexanes, heptanes, nonanes, and decanes that can often appear in formulations, and the number of components making up gasoline balloons. So we need a way to report on how resistant our fuel product is to detonation, but we can't simply use the composition of the fuel because it's far too complex and varied from one batch to the next. Now, the system that is used compares the detonation resistance of the gasoline product to that of a single pure hydrocarbon material, with N-heptane serving as a reference for 0 and isooctane serving as the reference point for 100. The detonation characteristics of motor fuels are so important that many additives have been tried over the past century to alter this characteristic. Of course, the most well-known and possibly calamitous of these additives is what is known as tetraethyl lead, an additive used to make so-called leaded gasoline beginning in the 1920s. This material, created by Thomas Midgley Jr. of General Motors and Frigidaire fame, helped to make fuel more resistant to detonation. The carbon-lead bond you see is fairly weak, and during compression, this additive will break down into species known as ethyl radicals. These radicals react with the combustion intermediates, delaying the onset of the combustion process as a piston compresses the air-gas mixture. And this allowed engineers to produce engines of higher compression or use lower quality fuels to get the same performance. That's wonderful. Sort of. The problem is that the tetraethyl lead also introduces lead into the system. And after combustion, this lead is scavenged by secondary additives and expelled from the engine. Not a problem in Midgley's day because the terrible toxicity and environmental effects of lead were not yet fully understood. But once it was realized just how dangerous this byproduct of Midgley's creation is to the environment and to humanity, it was very quickly banned from use. Now, a modern additive used to reduce premature detonation of fuels is methyl T-butyl ether, or MTBE. This additive accomplishes a similar effect to tetraethyl lead, delaying combustion to the appropriate time. But look at the structure. It doesn't introduce lead into the environment. Now, petroleum products have undoubtedly changed the world and how we obtain energy. Since Drake's discovery in Pennsylvania in the 1850s, it's been the go-to fuel for vehicles, furnaces, and many more creations. But it takes petroleum millions of years to form underground. And it's taken us just a couple of centuries to put a serious dent in the global supply. Since we use petroleum at a pace about 10,000 times faster than it can form, there is a serious gap in the renewability of this critical energy resource. In the past few decades, this notion has led many to consider what will happen if oil becomes too scarce or expensive to produce for the world's energy needs. When and if we will ever run out of petroleum is a very difficult thing to predict, since new deposits are always being located and newer technologies continue to make previously inaccessible or unrecoverable deposits available to us. Even so, when it comes to something as critical as the world's energy supply, it makes sense to think ahead and be ready with alternatives when and if oil can't fulfill all of our energy needs. One very attractive alternative to petroleum products is what has come to be known as biodiesel. Biodiesel is different than diesel in several different ways, but the most critical is this. Biodiesel fuel is created from natural plant oils extracted from growing plants. That means we can grow a field of raw material to make biodiesel in a single growing season, instead of having to wait an entire geological era as we do for petroleum. Let's take a look at one of those fats that might be used in a process like the production of biodiesel. Now, in this case, I'm using a relatively simple fat molecule here, a triacyl glyceride. It's called a triacyl glyceride because of these three acyl functional groups here. And they're holding on these long chains of hydrocarbon molecules that look an awful lot like some of the motor fuel molecules we've looked at previously. But they're all bound together through this connection here, these three acyl groups. Now, if I wanted to, I could chemically snip those groups using water in a process called hydrolysis. Using 3 molecules of water and an acid catalyst, I could run a reaction in which I interchange those groups, creating glycerin, which now makes a little bit more sense why we call them triacyl glycerides, right? And in the process creating what we would call fatty acids. But the problem with trying to get a motor fuel in this way is that fatty acids themselves are not that great at operating as motor fuels, because look at these polar groups here, right? These carboxylic acid functional groups. It's not a properly designed material. It's not going to work as a liquid fuel. So we have to use a slightly different reaction than a traditional hydrolysis. I'll show you what that is. What we use instead is called a transesterification reaction, which is a very, very similar reaction to hydrolysis. But instead, typically methanol is used. You notice here that instead of HOH, I now have CH3OH. So I'm using 3 methanol molecules here to react with my triacyl glyceride. When I do this under acidic conditions and transesterify my fat molecule, again, I get that glycerin molecule down there, but look at the difference. I have removed that acidic hydrogen from the end of my molecules. Now instead, there's a methyl group there. That's a hydrocarbon group. It's not acidic. So not only is it less polar and not acidic, but it has really great properties that are very, very similar to the molecules found in diesel fuel itself. If you don't believe me, just compare a molecule of this biodiesel that we just created to a molecule of cetane. This is made using palmitic acid. This is pumped from the ground and distilled from petroleum. Remarkably similar looking molecules, aren't they? And in fact, they are. They will have very, very similar combustion properties, volatility, and other physical properties as well. This amazing product can be used in many standard diesel engines without further modifications to the engine itself. So biodiesel offers a fuel that can be directly substituted for petrodiesel, but is produced from renewable, plant-based resources. Something to get excited about for sure. So let's sum up our short discussion on fuels. We started by defining fuels as materials that can be reacted with an oxidant to obtain energy. We acknowledge that the broader definitions of fuels exist, but that chemists tend to use this more specific definition. We took a look at the granddaddy of all fuels, cellulose, the biopolymer in wood and other plants which fuels natural wildfires and fueled early man's efforts to feed and shelter himself. Next, we talked a bit about pitch, or naphtha, a material that Greek and Persian empires found in scarce proportions near the surface of the earth, but which burned remarkably well. Modern chemists use the word petroleum to describe naphtha, and our discussion evolved as we met Edwin Drake and John Rockefeller, who helped contribute to the development of distillation and refinement techniques that make fuels like natural gas, propane, gasoline, diesel, and kerosene so readily available that they're often taken for granted in modern society. We also briefly considered the use of additives like tetraethyl lead and MTBE, which delay combustion to just the right moment in gasoline engines. But our discussion also led us to consider how petroleum is formed, that it takes millions of years to make and a relative instant to consume. So we talked a bit about alternative fuels, well, in particular biodiesel, a chemically altered form of plant oils which behaves so similarly to petrodiesel that it can often be used interchangeably. But our discussion of how man extracts energy from matter is not yet over. Today we focused on fuels, materials that can be oxidized under controlled conditions to steadily release heat and do work. Next time, we're going to up the stakes and discuss explosives, materials that release their energy not evenly and slowly, but in a violent event that can be harnessed to do immense good or catastrophic evil. Another interesting facet of the history of fuel chemistry came in World War I as Germany was trying to find ways to continue to fuel their war machine. You may recall Fritz Haber had a hand in helping them to acquire nitrogen to create things like bombs. But what about fuels? Let's try that out. Well, as early as World War I, German chemists were actually using processes very similar to the Haber process to create liquid fuels. For example, they could take graphite, which is essentially coal, react it with N+1 equivalents of hydrogen gas over a platinum catalyst, which we already know weakens that bond and allows it to react with the carbon better, to form all sorts of new hydrocarbons that could then be used in fuel applications. So essentially, graphite and the proper amount of hydrogen reacting over a platinum catalyst bed could create things like octane or diesel fuel. Of course, that fuel could then be reacted with oxygen in a number of engineered devices to create whatever they needed, right? Whether they needed heat or locomotion. Here we have an octane molecule reacting with 12.5 moles of O2 to create 8 CO2, 9 H2O, and of course, a considerable amount of energy. But that leads to a question. And that question is, if you're going to make octane from carbon, exactly how much feedstock do you have to put into that reactor? In other words, how much carbon does it take to make a certain volume of octane? Well, let's do the calculation here. Knowing that octane has a density of 0.703 grams per milliliter, let's calculate the volume of octane that can be produced from 1 kilogram of coal, assuming that coal is pure graphite. So this is the reaction that we'll be dealing with. This is just our generic reaction, but rewritten specifically for the production of octane. That's 8 graphite and 9 hydrogen gas reacting to form 1 mole of C8H18 or octane. So let's start with our kilogram of coal and acknowledge that we want to get to liters of octane. We're going to have to do some stoichiometry. Now, carbon weighs 12 grams per mole. And we also know that it takes 8 moles of carbon to create 1 mole of octane. Similarly, we can determine that it takes 114 grams of octane to make up a mole. And I'm almost there. Now I'm going to use that density, right, to get rid of grams of octane and get to liters. So here is my unit analysis. My grams of graphite cancel, my moles of graphite cancel, as do my moles of octane, grams of octane, and yes, I will get an answer in liters of octane fuel. So in this case, 1 kilogram of coal can be used ideally to produce 1.69 liters of octane. Well, that's great, but let's think a little bit more about this here. The combustion of a mole of octane releases 5,460 kilojoules of energy. But how much energy can we obtain from these combustible materials, the feedstock for this process, hydrogen and coal? We can burn those as well, right? And in fact, it's a very simple calculation to do if we know that the heat of formation of water is negative 286 kilojoules per mole and the heat of formation of carbon dioxide is negative 393 kilojoules per mole. The reason it's so simple is the combustion of these pure elemental substances is simply the same reaction as their heat of formation calculation would be. So here I just use 8 times the heat of formation of CO2 to get 3,144 kilojoules. And for my 9 moles of hydrogen, a similar calculation leads to 2,574 kilojoules. In other words, the same amount of carbon and hydrogen, if burned, will give me 5,718 kilojoules, more energy than I would get from the octane itself. So why do this? Well, for one obvious reason. Liquid fuels are required for many of the engineered devices that they fuel. And liquid fuel was so valuable that Germany was willing to pay an energetic price just to get it.